So continuing with our lecture notes, electrical forces are field forces. It's a second example of a field force. Gravity is the first one. Remember that with a field force, the force is exerted by one object on another, even though that there's no physical contact between them. So this is very similar to, there's a lot of similarities between electrical forces and gravitational forces, and obviously there's going to be some differences that we'll discuss as well. So if we compare electrical forces to gravitational forces, both are inverse square laws. The mathematical form of both laws is the same. It's just that we're going to replace the mass with charges. The electrical forces can be either attractive or repulsive. Gravitational forces are going to always be attractive, and then electrostatic forces are stronger than gravitational forces. An electrical field exists when we have a region of space around a charged object. So when another charged object enters this electrical field, the field will exert a force on that second charged object. The definition of electrical field: it exists in a region of space if an electrical charge is placed in that region and it's subject to an electrical force. The units are going to be newtons over coulombs. When we look at that equation, that QO is the test charge, and it serves to allow the electrical force to be measured. The E is the electrical field, the F is the force. So a charged particle with a Q produces an electrical field in the region of space around it. The small test charge, QO, placed in the field will experience the charge. And if we know the electrical field, we can calculate the force of any charge. That's what we'll be doing on our upcoming assignments. The direction of the force will depend on the sign of the charge in the direction of the field for a positive charge, and opposite that for a negative charge. The electrical field of a point charge will point away from the positive charge and towards the negative charge. The electron field produced by a negative charge is directed towards the charge. A positive test charge would be attracted to the negative charge. The electrical field produced by a positive charge is directed away from the charge. A positive test charge would be repelled because opposites attract and like charges repel. The test charge is required to be small. The electrical field exists whether or not there's a test charge present or not. And then the superposition principle can be applied to the electrical field if a group of charges is present. And the superposition principle will be one of the types of problems we will be solving on this unit. So an easy way to visualize electrical field patterns for problems is to draw the lines pointing in the direction of the field vector at any point. And this is called electrical field lines. It was first developed by Michael Faraday. We'll also be looking at magnetic field lines when we get to our unit of magnets. The field lines are related to the field in the following way. The electrical field vector is tangent to the electrical field lines at each of the points, and the number of lines per unit area through a surface perpendicular to the line is proportional to the strength of the electric fields in a given region. Now I know that doesn't make a lot of sense, but if we were in school and we did our magnet lab that I was planning on our doing, you would actually get to see these lines develop due to the magnetic forces. So on this one right here with the point charge, you can see that the lines are radiating out in all directions, and you can see that they are moving away from that positive charge. Now for a negative source, you can see how the lines are pointing inward.